guess we're still missing quite a few people, but maybe what we can do is go ahead and start. Um, so let me just briefly remind you what we were talking about last time. I gave you a couple of examples of the types of errors that we come across in a finite element analysis. So um, I was telling you that I think since we have two screens, I'm not going to be using the laser pointer, so hopefully this mouse should be visible to you all. So yeah, I was telling you that uh, for the analysis of any real system, you first try to build a mathematical model for the system, and in our case, it will be mostly solid and structural mechanics, the equations that govern the behavior of those kinds of systems. And then we try to discretize that mathematical model. That's the finite element model that we get. And once you code it up into a computer, that's the uh, numerical model that you get your solution from. So the important things were the types of errors that you get here. One is a physical error. There's nothing you can do about it. That's the best physics that we have. Uh, then the next step is the modeling error. That is the truncation error uh, that that you get when you discretize any mathematical model. And finally, on the computer, when you implement it, either you could have a bug or something. That's another type of error, but those are generally round-off errors. So I talked a little bit about the finite element history. I'm not sure how much of that you got, but um, the important things that I want to mention here is there are two types of approaches to that were traditionally developed. So one was the engineering approach uh, that follows this path, and there were two other approaches that came from mostly mathematics. One is the method of weighted residuals, and you should think of principle of virtual work when you think of weighted residuals. And another one was variational principles. So when you think of variational principles, you should think of energy methods. And I was trying to tell you how energy methods are related to the structural engineering approach, things like Castigliano's theorems and all that. All right, so today I'll talk a little bit about applications and also see a particular, also introduce to you the basics of some of the theory of elasticity. So this is a handout that I just sent around since um, there's not much uh, to do on the in form of calculations or anything. So here I'm just listing out some of the applications, structural engineering, geotech, hydraulics. We have all these different types of applications which finite element has been applied for. In structures, we have buildings, bridges, dams. A lot of times we build these finite element models and we try to analyze those things. In hydraulics and or geotechnical, you could have foundation and tunnels, hydraulics and hydrology. People try to model groundwater flow and subsurface flows. That's called hydrology with finite elements. And the objective in those kinds of problems is usually to try to figure out where is the best source for perhaps drinking water. So those kinds of things you can solve with finite element. Again, there are applications in mechanical engineering, electrical engineering. So really this is a very wide area. It has a very wide area of applications. And in general, basically, finite element is a very good tool for being able to solve different types of PDEs. And traditionally, you might not be inclined to think of your problems as PDEs, but essentially PDEs are what they are. So here is a little information about the types of PDEs that we commonly encounter. I'm not going to expect you all to, to understand the ins and outs of all the PDE theory, but it's good to know what types of PDEs there are in nature. So the three types that I've listed here are hyperbolic, parabolic, and elliptic. And I've given one example of each of those. For example, the hyperbolic example of a hyperbolic PDE is the wave equation. So for example, if you have some structure, let's say a bar fixed at left end, and if you hit it on the right end, there will be a wave that will pass through the bar and bounce back and forth. So the behavior of that is governed through the wave equation. And generally, hyperbolic PDEs are based on some kind of a conservation law. Okay. Parabolic PDEs, an example is transient heat conduction. Anybody seen a transient heat conduction problem, or do you know what that is? Okay, so I guess most of you don't know. So what, in a transient heat conduction problem, let's say you have an insulator, or if you're trying to, let's say you have an insulator which is this wide, and you have one temperature on one surface, another temperature on another surface. And if you try to figure out how much time it is going to take to equalize the temperatures, that's a transient heat conduction problem. So that's a parabolic problem. And these parabolic PDEs, they are usually dissipative. Okay. And lastly, there is this elliptic type of PDE. This is the type of PDE that we will be encountering mostly in this course. So static equilibrium of solids and structures, the governing equation for equilibrium that we have. PDE is partial differential equation. Sorry, I didn't mention that before, but so yeah. So elliptic PDEs are the ones that we will be dealing with. So listing out some of the examples of these PDEs. Hopefully, the first one here, the beam equation, everybody should be familiar with. So this is the governing differential equation for a beam. Let's say that beam is aligned along the x-axis. The vertical displacement is W at a given location x, and it is being acted upon by a load, distributed load Q. So the equation that governs the displacement of this beam along the x direction is EI W4 prime if EI is constant is equal to the load applied. And you can solve that equation. So how many of you think this is a PDE, or can we specialize it even further? Is this a PDE, or can we say that this is an ODE? ODE meaning ordinary differential equation. So this is actually an ODE because the only derivative is with respect to x. This prime represents x, right? So this is the most basic equation that you should all be familiar with. Now this type of equation is used in a theory that's called Bernoulli-Euler theory, and we'll go over more details about this theory later on in the course. And the other type of theory that we have is a Timoshenko beam theory. So did you guys cover this last semester, maybe in 570? Towards the end? Okay. So in Timoshenko beam theory, the important thing to remember is that that is a thick beam, so shear deformations are not negligible. In the Bernoulli-Euler beam, it's a pure, the deformations are always in a pure bending state. But in a Timoshenko beam, you can have bending and shear deformation. And I'll tell you more about this when we get there. But the governing equations for that Timoshenko beam, if you have the mechanics book, this is what the governing equations look like. But truly the first PDE that you will, one of the first that I'm mentioning here is this plate equation. So how many of you have seen this plate equation before? Okay, very few. So this is what is called the Kirchhoff-Love plate theory, and this is very similar to Bernoulli-Euler beam theory. In the Kirchhoff-Love plate theory, you do not have any shear deformations again. All the deformations are in a bending state. And on the other hand, you have the Reissner-Mindlin plate theory, which is similar to the Timoshenko beam theory. So in the Reisner-Minlin thick plate theory, we allow for shear deformations. Okay, and again, we will talk about these theories much more in detail later in the course. But a couple of other PDEs that I've mentioned in this handout are uh, equations of that govern the behavior of any continuum. It can be a solid, fluid, gas, whatever. So as long as you can represent your continuum, represent your material as a continuum, the equations that govern that behavior are these three: conservation of mass, conservation of momentum, conservation of energy. And this conservation of momentum equation is the one we will be using most often for solids. Okay, solids conservation of mass is mostly automatic. Energy, that is mostly contained in your material model. So for solids, we'll be mostly concerned with the equality or the conservation of momentum. Okay, and there are other PDEs also. We could just go on and on, but so let's. This is just a little talk about the applications of FEM. And if you are still not overwhelmed, let's go back and take an example of how we can apply finite elements to a problem that we are most familiar with. Let's say a problem of structural analysis and design. So try to imagine, a couple of years from now, you've all graduated and you're sitting in your office and some rich guy comes and asks you to build a bridge, across this valley. So what are the types of questions that you would ask them? You are a structural engineer, somebody comes to you and asks you to build a bridge or design a bridge across this valley. What kind of questions would you be asking?
Hydraulic.
Sorry?
Hydraulic.
Hydraulic requirements, okay. What are the hydraulic requirements for the bridge? Any other? Okay. What type of bridge? Anyone else? Sorry? Earthquake information. Expected loading, very good. So let's call it loading. So yeah, these are all, obviously this is a very general problem, so 10,000 questions might come to your mind, right? So let's focus in on some of the structurally related questions. So one question is what type of bridge we should choose and what type of loading should that bridge be able to support, right? So what types of bridges do we usually have?
Beam.
Okay, that's a beam bridge. So that's a simple slab on beam bridge. Any other? Suspension bridge. So this is a crude drawing of a suspension bridge. Any other bridges? Bridge, okay. Arch bridge, great. Anything else? Stable state? So any other types of bridges? Side arch. Okay, so that's a combination between suspension bridge and a arch bridge. Yep. So those are mostly the main kinds of bridges that we have. So now what? What do we? How do we go about designing a bridge? So our design philosophy usually is, you know, we will try out different cases. So trying out means we will assume a solution, and we will see if it fits the problem, right? So that's our design philosophy. That assume a type of bridge and check your solution. So next thing that we are concerned about as a structural engineer is loading. So what types of loadings can we encounter for bridges? Traffic, that's live load. Obviously, if there is live load, there's going to be dead load. There could be earthquake loading, wind, snow, and temperature changes. Stream and ice. So that's your hydraulic loading for the bridge. Anything else? Impact, blast for special cases. Fatigue loading is some sort of a material related loading. So yes, if your material degrades, it will in turn cause what we will interpret as loading. So sure, we'll put that out. So in effect, what we are saying here is that our bridge should be able to sustain all these loadings, and not just all of these loadings. If you go back and take a look at your design handbooks, there will be different types of combinations of these loadings, 1.6 times dead load or whatever those factors are. And in addition to all that, we have to make sure that all these loadings can be sustained for some amount of time. So let's say 50 years. That's our design life for the bridge. So this is the types of loading that these are the types of loading that our bridge can sustain. Now, how do we go about designing this? What are our design criteria that we use? So I'm sure you've already learned, usually we have two types of designs: allowable stress design and LRFT, which is load and resistance factor design. So these days, mostly people use the load and resistance factor design, right? And the philosophy behind that is that this equation should always be satisfied. right? So what we do is we come up uh, with a with a design, and we check that some factor. This is the uh, load safety factor, and L is the uh, the stresses that develop in your structure. Phi is the strength reduction factor, and R is the internal resistance of the material. So this is a crude equation, but in general, this is our design philosophy. We assume a solution, and we try to check the solution against these, uh, this type of an equation. All right. So let's try to do this for the simple, let's say a simple beam bridge or a truss bridge. So let's choose this beam bridge or this truss bridge. And there's some distributed loading, or whichever way you want, you can represent that loading. So what do we do to analyze uh, these systems? Basically, what I'm asking you is, what type of analysis should you be using? Would you be using a force method or a displacement method? Um, or so does anybody remember matrix structure analysis? Can we use matrix structure analysis, let's say for this truss bridge here? So for this truss bridge, can we use matrix structure analysis? Um, Matrix structure analysis would qualify as what we call a displacement based method, right? But right now, how do we do truss analysis? If we are given a truss and if it is determinate, we could go method of joints, or we could go method of sections and try to find out all the internal forces, right? And that would qualify as a force method, right? So the point that I'm trying to make here is that you cannot do displacement based method unless you actually assume some material properties. So right now you have just the outline of a bridge. So the first step in any analysis is always a force method. So analyze with force method. And once you analyze with a force method, something like method of joints or method of sections, then you know all the internal forces in each and every member of the truss. Then you can go to your design handbook, pick out a section that will satisfy that, that type of loading. And then once you have your material, your geometry and everything ready, then you can go in and do your displacement-based method. So after you've analyzed it with a force method, the next step is to refine your design with a displacement-based method. And the reason that we need to do things in this order is because for a displacement-based method, something like a matrix structure analysis, you have to assemble all these small stiffness matrices, right? So in order to assemble all these stiffness matrices, you have to know the material properties of each and every truss member. Then you can assemble those stiffness matrices. And finally, within the displacement-based methods, we have FEM. So this is where FEM fits in the big scheme of things. It's a method of analysis. It's a displacement-based method. It's a displacement type of method. And once you have your structure and all the material properties defined, then you can build a model and analyze it. Okay. Um, so a couple of other points about the design problem. Once you have uh, once you have a design, let's say design parameters, that how many members should be there, how thick each member should be, those are all called design parameters. Then you can go and set up your problem as an optimization problem. And FEM can also be used for optimization. So what kind of optimizations do we typically do when we are designing structures? One thing is obviously we want to save material, right? So sure, we want to save material and cut cost. Anything else? Um, Space, what do you mean? Okay, yeah, space and maintenance issues and all those kinds of design parameters come in. But structurally related, what I would say is we also want to be able to design it in such a way that not only would it withstand all these loadings that we talked about, but also if there were situations where all these loadings are exceeded, people talk about extreme loading scenarios and all that. In those cases also, our structure, maybe it would sustain some level of damage, but it would still function to a certain level. So that sort of gets into performance-based design. So this is some sort of an overall picture that I wanted to give you where FEM fits, how you can use finite elements to do a design and analysis of your systems. So now that we have gotten to analysis, let me more accurately set up the analysis problem. So um, so I'm going to mathematically formulate the analysis problem. Okay. So let's say we have this beam, and I'm not going to represent it as a one-dimensional beam. I'm going to represent it as a two-dimensional or a three-dimensional structure. Real life is three-dimensional, so let's try to assume that this is a three-dimensional long beam, and it has all these different types of loading. So the problem that is given to us is geometry is given, the geometry of the structure is given, the loading is given, and after a force-based method, after an analysis through a force-based method, we also have assumed certain material properties. So we know the material properties of this beam. So what would a solution look like? What are we solving for? When we say we want to analyze a structure, what are we trying to solve for? Okay, so displacements is one of the primary variable. So let me represent the displacement by U, but what displacement are we looking for? Displacement of the beam, can we say of a certain point, or what are we looking for? In the middle, sorry? Say that again, I'm sorry? critical sections. Okay, so yeah, those are all good answers. But what we are, what I'm trying to say here is the displacement you want, the full analysis problem would be that you want the displacement at each and every point in your entire structure. That that is the full formulation of the displacement problem. And what I mean by that is, let's say this displacement is a vector, and I'll talk a little more about vectors. So I want you to tell me this displacement as a function of x, which is also a vector. So let me draw that. Let me place my origin, and so this is the origin, and let me call these unit vectors ex, and let me actually not call them small ex. So now I'm actually starting to follow some sort of a continuum mechanics notation. So if something is not clear, just raise your hand, let me know immediately. So this is the origin. This is a unit vector in the x direction, unit vector in the y direction, unit vector in the z direction. And if I go to some point in the beam, let's say here, the position vector of that point in the beam I'm going to denote with big X. Okay. And here's another note about this notation that I'm using. All the vectors I'm going to denote by underlining their symbol. All the scalars will be just without any underline or anything. So okay, so now this is the position vector that was before deformation. Okay, now I'm going to try to draw this beam after it has deformed. So, and I'm going to exaggerate that deformation quite a bit. So let's say the beam deforms and comes to this place. Okay. So the point that was originally, this point that was originally at this location X will move to a new location. And let me call that location small x. And let me denote that vector with this blue line. So this vector that goes from the old location to the new location is your displacement. This is u as a function of x. And this is something that hopefully you should have seen before. But if so, to state the problem once again, if I give you a geometry, give you the loading, give you the material properties of a structure, you have to be able to tell me the displacement, this displacement u of each and every point everywhere in the beam. Where does this point x go after deformation? So just to give you an example what this deformation could be, as an aside, if I say ux, let's consider a two-dimensional case. Let's say a ux, uy, which is both, actually let me make it three-dimensional since I'm talking about three-dimensional things. So this is a three-dimensional displacement field. And each of those components are actually functions of big X, big Y, big Z. So this is how we typically represent a displacement field. You have, you can have displacement in the X direction, displacement in the Y direction, displacement in the Z direction of any point. So if you give me a point X, let's say this point X, then I can plug that value of X into this function, and I can obtain what is the displacement of that point x. Okay, so this is the displacement map. Um, so let's say if this displacement of as a function of x is equal to x, and let's say my original material was this block, this unit cube. So this is my unit cube, and if I give a displacement of ux is equal to x, can somebody tell me what would this look like after deformation? So each point x should go to x plus x, right? Because what we have here is that displacement is actually equal to x so the new location, this new location small x, this new location small x can be represented with x, this old location, plus the displacement. So that's the vector equation that I've written out here. So if I'm saying that ux is equal to x, then the new location of the point would be just 2x, right? And what that means is that after deformation, this will just become a cube of side 2. Instead of a side 1, it will become, so this side was 1, this side is 2. So this is basically what we are trying to do here, is trying to describe the deformation of material. This is your displacement map. If you give me x, I can tell you where it went. So this is a displacement map. All right, so coming back to the analysis problem. Now that you have the geometry, you have the loading, you have geometry, you have material properties and everything, you want to find ux. So what equation should we solve? What equation should we solve to find out ux? So, okay, so I guess whenever you're in doubt, try to relate your problem to something that you already know, okay? So how about this problem? So again, another aside. Let's say you have this two-spring system, and I'm applying a force Fx in this direction, and I'm applying a force Fy in this direction. And after deformation, perhaps the springs, this point goes to somewhere here. So the springs would be something like this and something like this. Let me call this theta 1. Let me call this theta 2. And now if I try to write out the equation of equilibrium, this is Fx, Fy. So if I draw the free body diagram of this point, that point is being acted upon by this force Fx, Fy, and there is one spring force. Let me call these spring constants K1, K2. So this spring force is Fs2, and this spring force is Fs1. So if we write out sum of forces in the x direction is 0, sum of forces in the y direction is 0, that will give me two equations, and then I can find out my displacement. That would be u, and v. So is this problem something that you have done before, right? So in addition to this, there's a couple of other unknowns also, fs1 and fs2, but we know from material properties that the spring force in 1 can be represented with its spring constant times whatever extension it undergoes, delta 1, right? And delta 1 is a function of u and v. Similarly, fs2 is k2 times delta 2, which is also a function of u and v. So the only unknowns here are the displacement in the x direction, that is u, and displacement in the y direction, that is v. And all we need is two equations of equilibrium that say sum of forces in the x direction is 0, sum of forces in the y direction is 0. You have both of those as your equilibrium equations. So the point that I'm trying to make here is, in order to find displacements, you were using equations of equilibrium to find out how much displacement is there. So now going back to this problem, in order to find this displacement field, what equation should we be solving? I just told you it has to be an equilibrium equation. What is the equilibrium equation for each and every point in this body? Does anybody remember? I'm sure you remember, but you're hesitating to say. Okay, so was that? Yeah, that's right, div s plus b. And I'm not going to assume. Let's try to see how we can come up with that equation. So try to imagine a small block, a small cube here at the new location. And keep in mind that I'm choosing a small block in the new location because here also, in this example also, in the spring example, we chose to enforce equilibrium in the deformed configuration, right? Equilibrium does not hold in the original configuration. After you apply the forces, it will deform and go to a new location. So equilibrium has always to be enforced in the deformed configuration. Okay, so that's why I'm choosing a small block of material that's just around this x in the new location, and I'm going to try to write out what equation of equilibrium we should have at that point. Okay, so just keep in mind this small block, and let me zoom in here. So let's say that that point is right here, that point x, and I'm going to draw a cube right around it. And I've messed up the point a little bit, but okay, so let's say this is the point and this is the cube around that point, and this cube has dimensions, and I'm going to rename the unit vectors around this cube. So E small x, E small y, E small z. These are my unit vectors in the deformed configuration. And let's say I'm considering this small cube. So this is delta x, delta y, delta z. Okay. And since this is a cube, it has 6 faces. So let me name those faces. So I'm going to call face 1, which is the positive x face, face 2, negative x face, face 3, 4, 5, and 6. So these will be both positive and negative y faces, and positive and negative z faces. So now I'm going to count on some background of solid mechanics that you might have had. If you go to the center point of this face, this face right here, this is the positive x face. So the positive x face is the number 1 face, and if I go to the center point of that face, then I can represent the tractions that are acting at that location by something that should be familiar to you: sigma xx, sigma yx, and sigma zx. And since these are tractions on the positive x on the face 1, therefore I'm going to increment them or attach a superscript to these faces such as 1. Okay, and the same thing I'll do on the back face, which is face 2, on the negative face. But on the negative side, all we have is sigma xx on the face 2, pointing in the negative x direction, sigma yx in the negative direction, and sigma zx in the negative direction. So similarly, you all remember, hopefully you can place these tractions all over the 6 faces of this unit cube. Not a unit cube, sorry, it's a infinitesimal cube, because it has sides delta x, delta y, delta z. So now if you do that, and you should note that you can represent sigma xx on the first face in terms of a Taylor series expansion. So sigma xx on the second face plus del sigma xx over del small x times delta x plus higher order terms. Right. So all I'm doing here is I'm expressing the state of stress on the middle point on the first face in terms of the stress in the middle point at the back face. So the only change here from the back face middle point to the front face middle point is this delta x. So that's why the Taylor series expansion can be represented as this sigma xx1 is equal to this sigma xx plus the rate of change of sigma xx times delta x. So this is a first order Taylor series approximation for sigma xx1. Similarly, you have 2 other approximations, which are sigma yx1 would be equal to sigma yx2 plus del sigma yx over, so this is something like here, sigma yx over sigma y times delta y. Actually, this is sigma xy. And similarly, you have sigma xz, and on the first face is equal to, sorry, I think I've, okay, let me redo this. And what is the time? We're just about out of time. So what I'm trying to tell you here is that when you do this, you get 3 sets of equations. Let me write those out, and then I'll fill in the blanks next time. So the 3 sets of equations that you get are this: sigma x y over sigma y plus sigma z x z over sigma z plus bx is equal to 0. Does this equation seem familiar to you? This is the equation of equilibrium in the x direction for this cube. For this cube, and this cube came from this point in the deformed configuration. So if you want to enforce equilibrium of anything, all you are trying to do is go to the deformed configuration, draw a small rigid body. All we are doing here is we are drawing this rigid body, marking all the forces that are acting on it, and summing them up to 0. So this is nothing but the Newton's first law. And what happens when the sum of forces is not in equilibrium? Let's say sum of forces is not 0, then we have acceleration, right? So ideally, we can have this term in terms of dynamics. So anyway, let me call it a day at this, and then next time I'll fill in more details about this. I'm also going to assign a homework based on this cube problem, and you will have to show me that indeed these are the equations that you get. So I'll post that homework tonight, and you'll have until next week, next Friday, to complete that. There is also a MATLAB assignment in that homework, and maybe another problem. Okay? All right, so see you guys Friday. And by the way, this room change is permanent, so next time and every time onwards, we're going to meet here. All right?